Hello everyone, I'm Tianxiang from Shanghai Jiaotong University. Thank you to the organizing committee for giving me this opportunity to present our research. My presentation topic is all-day free space quantum key distribution with continuous variables. In the field of discrete variable quantum key distribution, there have already achieved QKD using free space channel via satellite. In 2017, Pan Jianwei group achieved 1,200 kilometers satellite to ground QKD, and in this year, they accomplished 12,900 kilometers QKD between China and South Africa. Continuous variable quantum key distribution provides an alternative way to share secure secret keys. CVQKD inherits the advantages of cost-effective and high-speed solutions of coherent optical communication to realize high secure key rates. The ideal implementation of CVQKD can approximately reach the PLOB bound, which gives the ultimate limit of secret key capacity of repeatless quantum communication. Compared to DVQKD technology, CVQKD started later and is less technologically mature. The experimental studies of CVQKD mainly focus on fibre channel implementations, both in library and field tests. The longest distance free space CVQKD experiment known was reported at a 2017 conference, achieving a communication distance of 1.6 kilometers. The longest published communication distance recorded is 860 meters polarization encoding experiment conducted this year. We have achieved CVQKD over 7 kilometers of urban atmospheric channel in Shanghai, China, and 9.6 kilometers of marine atmospheric channel in Dalian Bay, Dalian. We use the IQ modulator to perform Gaussian modulation of the optical field and employ homodynamic detection for coherent detection of extremely weak quantum signals. Our experimental implementation mainly relies on 5 key technologies for free space channels. The first key technology is channel flexion independent dynamic polarization control. We select a 10% quantum signal and calculate its ratio to local oscillator to provide feedback independent of channel loss flexion. This graph shows the power of signal light and local oscillator light after activating dynamic polarization control as well as polarization isolation. The second technology is phase compensation. Two adjacent high-intensity QPSK pilot pulses are employed to celebrate one quantum signal. The signal phase due to homodynamic detection, where the X and P components of one QPSK pilot state are encoded in two adjacent QPSK pilot states to reconstruct the phase drift. The third key technology is data synchronization. The local oscillator is oversampled by a factor of 200, which enables the signal pulses to be captured as comprehensively as possible and the pink point to be closely approximated. Furthermore, by calibrating the delay between the signal path and the split motoring path in advance, the pink data of quantum signals can be precisely extracted. The fourth key technology is channel transmittance grouping. We group the data according to channel transmittance to calculate key rates. We use 0.2 decibels intervals as subgroups. In this graph, green represents channel attenuation for 7 kilometers urban atmospheric channel, where blue represents 9.6 kilometers marine atmospheric channel. The corresponding channel flagship access noise for each subgroup is shown in the graph below. After calculating the key rate for each subgroup, we perform a weighted summation to obtain the final key rate. One experimental result is shown in the bottom right, where the right indicates subgroups with secure key generation, and the yellow indicates subgroups without key. The fifth key technology is ATP technology. We designed and built an ATP system for signal transmission and reception in most atmospheric case. For 7 kilometers distance, this ATP system can control average channel attention within 18 to 25 decibels, and for 9.6 kilometers distance, within 24.9 to 32.7 decibels. This is the actual experimental setup for the 7 kilometers urban atmospheric channel. The left side shows the experimental environment and the perspective view at the sending terminal, and the right side shows the receiving terminal. We conducted the experiment between Minhang District and Songjiang District in Shanghai. The experimental results are shown in this figure. The left figure shows excess noise, and the right figure shows the key rates. Different colors represent data from different days. More detailed experimental data is listed in the table below, including channel attenuation, subgroup proportion, modulation variance, electronic noise, signal-to-noise ratio, excess noise, valid data proportion, reconciliation efficiency, frame error rate, subgroup key rate, and weighted key rate. The subchannel key rate is approximately on the order of 100 bps with a maximum weighted key rate of 2.3545. This is the experimental setup for the 9.6 kilometers marine atmospheric channel. For the marine atmospheric channel, almost all data came from daytime. This is likely attributable to the climatic conditions of the marine environment during that season, where temperatures decrease and humidity increase after sunset, leading to the emergence of turbulence and formation of fog over the sea, making it difficult to obtain valid data in night. These are the experimental results. Here are the corresponding excess noise and key rates along with the detailed data. The subchannel key rate remains on the order of 100 bps with a maximum weighted key rate of 0.4768. The last page shows excess noise analysis for the 7 kilometers urban atmospheric channel. We analyzed the various common sources of excess noise in current lecture. In our experiment, the main source of excess noise is contributed to phase noise, accounting for up to 90% of the total noise. This is our research team. Thank you to everyone who helped me. We sincerely thank you our partners from Xuntai Quantum, Guangdong CS Quantum Network Company Limited, and the University of Science and Technology of China for their valuable collaboration. Before we move to question and answer, I would like to honestly say I have practiced this talk many times because my spoken English is quite limited. I'm afraid I may not fully understand your question during the discussion. But if anyone is interested in my research, I would be very happy to discuss it with you. Maybe use a translation app. Thank you for listening.